Imagine an invisible compromise moving through a server environment at high speed. The internal state of the machine is actively being dismantled and rearranged, yet all the system logs report normal, authorized operations. In this specific attack scenario, the conditions are pristine. The user's prompt is perfectly clean, containing absolutely zero malicious instructions. The core task assigned to the AI agent remains entirely unchanged from start to finish. Despite these secure baseline conditions, the deployed AI agent fails and executes an unsafe action 85.0% of the time. The engine driving this failure is a black box system called EMHA, or Evolutionary Markov Hypergraph Attack. It runs without touching the prompt and without altering the model's parameters. If an adversary can reliably force a catastrophic failure while feeding the model completely benign instructions, the prompt injection filters we rely on are watching the wrong door. The researchers achieved these numbers inside a custom red teaming arena called OpenART, designed specifically to test long-horizon agent behavior. They evaluated this attack across a massive corpus of over 10,000 validated stateful scenarios spread across 50 different domains. These are highly complex tasks. The arena draws from a pool of 500,000 unique tools and skills, with the median task requiring an agent to execute 97 separate tool calls to reach completion. The target list covers 75 different configurations. It tests 15 deployed agents, including Copilot CLI, Claude Code, and Aider, wrapped around 5 different foundation models. Testing at this scale exposes a critical blind spot. Current safety benchmarks rely on short, static tasks that fail to simulate the complex, multi-step reality of deployed agents. EMHA operates through a mechanism called feedback-driven environment evolution. It analyzes the agent's behavior and continuously alters the surrounding environment to push the agent off course. The attacker strictly uses authorized state transitions. Every single modification it attempts must map to a native location and pass all runtime validations. Nothing it does looks like an exploit. This diagram outlines the exact surface area exposed, 8 writable vectors connecting to the agent, including memory, workspace, and tools. Run after run, EMHA iteratively rearranges legitimate files inside these nodes, keeping whatever arrangement causes drift. Traditional prompt injection filters see absolutely nothing. The agent isn't being tricked by what it's told to do. It is being poisoned by the state of the room it's forced to work in. Passing a static safety suite often gives engineering teams clearance for deployment, assuming the agent is secure. The data from OpenART proves this assumption false. This plots attack success rate against task complexity. Down in the bottom left, on simple environments, the attack maintains a 2% edge. But as dependency depth and tool call count scale up, the attacker's edge grows to over 17% on the most complex tier. The gap between static benchmark safety and actual stateful safety widens drastically. A certification on a short task provides zero guarantee for a 97-step workflow. When an agent fails, we have to isolate the architectural fault. We need to know if the vulnerability stems from the foundation model itself or from the software harness wrapping it. This chart breaks down the attack success variance. 91.3% is dictated by the foundation model and basic task completion, the vast majority of vulnerability. But the specific runtime implementation, the harness, explains an independent 7.6% of the failure rate. We previously covered how an agent's capability is driven almost entirely by its harness, but for safety, the math runs in reverse. While the harness plays a measurable role, safety remains heavily dominated by the model. Choosing an agent framework is a security decision carrying a 7.6% variance penalty. This choice impacts safety as significantly as any ergonomic preference. We have to look closely at the methodology producing these numbers. The 85.0% failure rate was generated by the exact same researchers who built the arena. Their scenario admission rule dictates that every single scenario in the 10,000 task corpus was pre-selected. A task only enters the arena if the authors guarantee a reachable, detectable, unsafe outcome. Stating agents fail 85% of the time describes a hit rate on a highly curated, vulnerable distribution. It is not a baseline reality for the safest models in production today. For engineers building these systems today, the immediate takeaway is defensive. You cannot rely on prompt filtering to secure a complex runtime. This research forces a shift toward a concept called state provenance. state provenance requires you to rigorously audit which specific parts of the operational environment your agent trusts by default, and trace exactly where that data came from. You can use the 8 EMHA attack vectors as an immediate audit checklist. Review your workspace, plan state, and memory to determine exactly who or what other processes have write access to your agent's configurations. The next necessary step for the field is an independent cross-lab replication. We need to see if this high vulnerability holds when EMHA is run on scenarios that haven't been filtered through OpenART's own admission pipeline. Until agent frameworks can guarantee the provenance of their own operational state, long-horizon AI agents will remain inherently vulnerable to the rooms they work in. If you found this breakdown useful, subscribe for more technical analyses of AI research and architecture.